Yeah, I'm sorry. Good afternoon. I would like today to tell you a story about the research we have been doing in our laboratory over the last 6 years. I've been always interested in Raman spectroscopy. Been always interested in Raman spectroscopy. That is very interesting field. Look, for example, at this example. Diamond, a very big crystal, has extremely simple Raman spectrum. I will show it in a moment. But you can consider something else, adamantane. Adamantane is a very small crystal of diamond, the smallest you can actually imagine. The connection between carbons is exactly the same like the diamond crystals. However, the spectrum of adamantane is extremely complicated. Well, maybe not extremely complicated, but quite complicated. That's the Raman spectrum of adamantane. But if you look at the same spectrum of diamond, it consists of a single line, just one line. And now the question is, how is it possible that going to larger system, more complicated in a sense, the spectrum gets so much simpler? The answer is easy if you look at the solid state physics theory. For a diamond, if you look at the first Brillouin zone, the only place where the actual, I tried to remove this frame last time, okay? By disconnecting Zoom and connecting it again. Good. Okay. The first Brillouin zone of diamond has quite complicated shape, but only one point of this Brillouin zone located around gamma point contributes because of the selection rules related to the energy conservation and momentum conservation. Now, if you look at the larger crystals, I started with adamantane and going to larger and larger crystals. You have a series of nanodiamonds that finally, at the end of the day, should converge to the spectrum of diamond. When you look at this, you can actually make the simulation. You see the convergence. You see a number of peaks that for the lowest, for the smallest crystal here, that's quite complicated spectrum, getting more and more complicated for the larger ones. But finally, at the end of the day, at the structure called O8, which, as you see on the previous page, has around 1,000 carbon atoms. At the end of the day, it converges to something that is dominated by a single peak around 1,200, and a group of peaks converging slowly, very slowly to zero. And when you look back at the diamond, you see that would be exactly the spectrum that you would expect. One group of peaks located at the optical corner and one at the acoustic corner. This is even more interesting if you go to larger nanodiamonds that we couldn't model, but we could measure in experiment. In a paper published a few years ago, we took a nanodiamond of the size of 68 nanometers, and then really shows a single peak like a big crystal. If you go, however, to a smaller one, 3 nanometers, which contains huge number of atoms that we cannot model, you see that the peak is actually consisting at least of 2. You can be deconvoluted into 2 signals. And if you look at these signals, you can think what's happening. And then you can again come back to this picture of solid state. And when you enlarge this point, this gamma point, you see we don't have an infinite large crystal, but a finite crystal. You can convolute it together with some Gaussian that involves larger area around the gamma point. And that's why contributing to the bend on the both sides. A lot of interesting research can go along that line. One of them is, for example, checking when the Raman spectra of finite polymer chains will converge to the infinite polymer chain. And you see that depending on the number of carbon atoms in them, you can get larger and larger chains with activity, Raman activity, that are kind of converging to a constant. However, this is just an introduction. telling you that I've been doing many different research along the Raman spectroscopy line. And maybe 6 or 7 years ago, I was knocking on my door in my office, and Professor Hiro Kamaguchi, a colleague from my department, editor of the Journal of Raman Spectroscopy, came asking me if I would like to co-advise a new student that is joining his laboratory, Ankit Raj. And that turned out to be a great idea. I was very happy to agree. And we started co-advising him. He was suggesting what to do experimentally. I was telling you how to match it with theoretical calculations. Ankit had one dream. His dream is to introduce absolute Raman spectroscopy. If you go to experimental data, usually the IR spectroscopy on the y-axis has a unit, but on the Raman spectroscopy, it always says arbitrary units. And I didn't really understand why at that time. Only working with Ankit, I realized how many different steps must be fulfilled in order to put actually some units there and numbers that are absolute. And Ankit's idea was to develop such absolute standard. And that involves a lot of different things. Here's again some experimental work related to that thing. Ankit repeated a very simple experiment. He took a benzene molecule and one particular line at 992 wave numbers, and he was measuring this line intensity for 4 months, doing millions of experiments. Well, maybe not millions, but hundreds of thousands of experiments. And every dot here is a 15 seconds measurement of the spectrum integrated over that peak. And what he found is that these Raman spectra are extremely sensitive to different things. That's the temperature in the lab, humidity in the lab, pressure in the lab. And each of these experiments is kind of traveling in this three-dimensional space. And then, as you see, he has around 12 pieces, 12 different colors. It means he was doing this 4 months, not a continuous experiment, but on 12 different days. The longest one was 40 hours. The shortest was, I believe, 2 hours. And every dot on the right-hand side show one experiment results for a single measurement of a single peak of a single molecule. It's really boring, but he was very persistent to do that. And what you see is that position of these peaks is waving. You have around 0.6 wave numbers drift. Next thing, the intensity of every Raman band is waving too. It's plus minus 3%. So there's a lot of problems with experiment to get the accuracy better than 3% on the intensities, and also to lock on the position of the peak. Good. He was doing a lot of other things. For example, he explained me that if he has a Raman spectrometer like that, he has to calibrate it. And calibrating means checking how much intensity from a given wave number comes to the detector. And I asked him, what it really means? He said, every optical element has its own characteristic. For example, look at these two elements. This one has different transmittance, changing by 20% depending on polarization and on the wave numbers. This mirror has different reflectance depending on the wave number. Now, when he's measuring a spectrum, just counting how many photons come to the detector is not enough. You need to have a good theoretical source of estimating what the intensity should be, and only then you can make a tuning for every pixel in the detector to observe the correct number of photons. And this is hard. This is hard theoretically and experimentally. And his idea was the following one. Let's take the simplest system we can actually calculate, H2. And this H2 has many row vibrational lines. And these row vibrational lines are located between 200 and then the 1200 wave numbers in the Stokes region. If I take the intensity of these lines from theory, calculated very accurately, and compare what his detector is counting, the number of photons that come at every pixel, you can design a correction in the spectrometer he has. This particular one, this only unique machine he built with his own hands on his optical table, and he can actually make a very nice absolute Raman intensity scale on that spectrometer. And he said, after doing that, you can extend it. You can take, for example, a spectrum of O2, and you can do the same in the region around 16,000 wave numbers. So there are windows from every molecules that can be used for scaling every part of the spectrometers. This is very, very experimental so far, but now I come to theory. He asked me what it can be done, how to calculate this intensity from theory. And we started by analyzing H2. We went to the static polarizability of H2, checking which method we have to use and which basis set we have to use. And as you see, these are bases starting with triple zeta, quadruple zeta, going to 8 zeta bases. And I'm showing how the parallel and perpendicular component of the polarizability tensor are converging. They are converging very slowly. If you want results that are converged to within 1% of theoretical thing, we have to take huge basis set. On the calculation method, in this case, was a couple of clustered singles, doubles, but in the case of H2 is simply CI, so there was no limit on the excitation level, just the size of the single electron basis. So that was not enough. Finally, we have to design a basis that not only had sextuple zeta augmented quality on each hydrogen atom, but in 5 different locations between the hydrogen atom, there are 5 mid-bond functions containing 8 s orbitals, 6 p orbitals. This is huge basis, probably very large, one of the largest ever performed for H2. And only that gave us a quality that was acceptable in this particular geometry. This is an equilibrium. Now we wanted to check if this equilibrium convergence works outside. So we checked how the polarizability is changing with respect to the internuclear separation of 2 hydrogens. And we can see that the smaller basis set, triple zeta, does terribly. Quadruple is converging. Only our basis with these additional mid-bond functions given by these black dots is not doing perfectly, as you see, but it's doing relatively well over all range of internuclear distances. There is still space for improvement here. Good. With this basis, we are able to calculate not static, but dynamic polarizability. So mean polarizability and anisotropy of polarizability at different wavelengths of laser, at different internuclear separations. We calculated the surfaces. You can see here the back lines, red one and second. These are the static polarizabilities. The other one are dynamic, laser frequency dependent. Using that, we could go to the task he wanted to make a calibration of his spectrometers. And to do that, we used a very simple formula. We had 2 pieces. We had 2 pieces. One were the raw vibrational wave functions that again came from, these are non-harmonic, obtained on a numerical grid by solution to the vibrational Schrödinger equation. Using these pieces and using these polarizabilities, we are able to calculate the cross sections and the intensities. And that turned out to be very accurate. The red results here are results obtained over 20 years ago by using geminal basis, explicitly correlated calculations. And our results are the blue and the green. As you see from that, we are able to recover most of the results, except for a few points on the red one that lay off these lines. So we were checking results from these geminal calculations and turned out that it was published in the times when you copy the data by pen and by paper. So 1 times 6 was replaced by 8. 1 times the columns 6 and 7 were changed to 7 and 6. So because of this type of data, we are able to identify a few of the mistakes in the previous one. They are very good, they are extremely good. But my point is, with the electronic methods that are available in the packages, you can actually reproduce this at some effort and actually get it better, more reliable in a sense. Good. So we calibrated the intensity scale, but then Ankit wanted to move further. He wanted to move to other windows, not that one that H2 can do, but also where O2 and N2 are active. So what he asked is the following thing. When you do intensity calculation in any package, the so-called double harmonic approximation is made. In this double harmonic approximation, you assume that the vibrational wave functions are in harmonic potential, and you assume that the polarizability variation over that wave function is just a linear variation. And he asked, how true is this assumption? And we just did a test. Here we just kept only the linear component of polarizability, quadratic, cubic, and so on and so on. And we are able to show that the errors coming from keeping only the linear one gives a residual. This is 20 times larger than it really is, otherwise you wouldn't see it anything. But to make this residual go away, you really have to go to the cubic component. That was accurate enough. Then we ask, can we actually do calculations for other molecules than H2? And then we started testing these things. For H2, everything was clear, how it works, how the polarizability components change with distance. For the other molecules, we had problems. For example, we did the test for 5 diatomics here. And these 5 diatomic systems, you can see 5 different methods, usually 4. One for fluorine dimer, there is CCSDT. And what we found is that over the blue window signifies the vibrational wave function of the dimer, of the diatomic. Over the blue window, the polarizability not only is not linear, it has quite strong quadratic or cubic character, but the polarizability calculated with different methods is very different. And then we were thinking, why? Why is it so? And what can we do about it? How to choose a method that's actually reliable? So we did even more than that. We computed, that was the perpendicular one. This is the parallel one. In the parallel one, you can see that the F2 molecule polarizability is completely failing. We see that every different method producing very different pattern. That is probably related to the dissociation of F2 that cannot be described by any of this method well, except for CAS-SCF. So we just made a test how it looks on the longer scale. And this is the calculation with different methods of different molecules. So columns are different methods and rows are different molecules. And now the important part is that on the right-hand side here, you can see triangle. This is the theoretical limit to which the polarizability component should go. This is double of the atomic limit. And as you see, CAS-SCF almost always does converge to that limit. We don't know how good this CAS-SCF is, of course, because no correlation. But comparing to the other methods that diverge crazily, and particularly coupled cluster methods, unfortunately, to that, we see that out of these choices that we had to do the calculation, we had to choose CAS-SCF our limit. However, we are not expecting really good accuracy. So at the moment, Ankit decided not to use this data for calibration of the spectrometers, because probably the accuracy we would get here would be 10, 20%. That's not what he's interested. Having seen these results, I decided that maybe this is a good reason to show them to you, to people who are doing method developments. Maybe I can discuss with you how to do it better, or maybe if there are ways of computing distance-dependent dynamic polarizability of molecules that we could trust. Turns out that this double harmonic approximation, there's an error of around 5%. except for F2 when the error is very large, this because of the failing of the electronic theory methods to describe the dissociation pattern. And conclusions. We need reliable methods to computing distance-dependent dynamic polarizabilities. There are, in my understanding, we don't have them now. And maybe soon, at least for some range of Raman spectrometers, the Raman spectra will be given in absolute units. So what's Ankit plan? Now it's almost done. He has this one spectrometer that has absolute scale in the range between 0 and 1000 wave numbers. He can measure whatever he wants, any chemical on this scale, having peaks between 0 and 1000, and then he can publish a list that any other experimentalist in the world can measure on his own spectrometer and can make a scaling calibration of its own Raman spectrometer with that particular list of transitions to make absolute calibration. So these results will be published this year or next year. And I only wanted, I still have a few minutes, so I only wanted to say that for large molecules, we are also having a problem. The Raman spectra for large molecules are very bad. There were talks today, they were talking about calculation in double zeta basis set, triple zeta basis set, energies are converging nicely to the CI limit. Maybe, yes, maybe true, but experimentalists don't need double zeta. They need huge bases. They need huge bases that converge actually to the experimental results. I wonder how this can be achieved. Maybe this talk will stimulate that. I think I finish here. Thank you.
Okay, thank you very much. Please. Yeah.
Sure. So